Again, welcome to, we are in week 7 now, isn't it? I think we are in week 7, yes, of instruction. Next week is going to be really midway. We should be, in the entire, I think, course sequence, we have 12 chapters. By the end of this week, we would have covered 6 chapters. So we are really on pace to cover the entire content where it's supposed to be. I mean, because I know I'm counting also the time when we'll have to be tested and so on and so forth. So in very good shape, I think, to meet all of the requirements. We're also on schedule in terms of the labs per the syllabus. So everything is up to this point where we're supposed to be. The only concern I have for you guys is, and I really want to emphasize on this point, is to make sure that you guys are doing the work from your end, especially the homework. We have an exam that is next week, okay, and the focus is going to be actually on exam 2. You have assignments that are due by this Saturday, and they are all related to that exam. So I'm hoping that you guys will do those problems. Also, we have a quiz, which is really part of the evaluation process that covers the entire chapters that of this exam, namely 24, 25, and 26. That is also due by Monday, I believe. So all of these things are due before the exam. Then the actual exam is going to be different this time around. It's going to start a little early and give you enough time, hopefully, to go through it and answer the questions and go through all of the reviews and all of these things. If you discover there is an issue with the exam, and there might be, okay, because I create a lot of variations of the same exam, and in doing so, I may have some mistakes here and there. So please send me a message via Canvas as soon as possible. I will answer those things in a specifically designated discussion forum. What that means is that you guys need to subscribe to that discussion, because with any update, with any changes to it, you need to know exactly that they happen, because it's not practical to have a Zoom session open for that much time, because the exam is going to be an extended period of time. So that's the next best thing, and that is to have to be subscribing to that discussion forum so that you receive messages right away from Canvas and go there and check to see if there is something that relates to your exam, your version of the exam at least. Now, I stopped responding to those messages at some point because then they will be too close. So I will not be able to give any feedback. So try to go immediately once the exam is open. Try to go through it, discover if there is any issues. Like last time, for example, I put the microcoulomb, and I put the micro as being 10 to the power positive 6, whereas it should be 10 to the negative 6. As also was noted in another place of the exam, in the big header of the exam, there was all of these prefixes with their proper values. But during the exam, during the specific points in there, because it's no secret, I use a lot of scripting, and sometimes when you're writing code, you don't pay attention to some of this little things that hide behind a lot of basically script markup. So you need to pick up those things, please, as soon as you see them, and we fix them as soon as possible before it's too late, before we are very much advanced in the exam, and then somebody discovers something which is justifiably so, then a lot of people probably might be confused or something. So at some point, I will stop responding to those requests on the discussion, but please do ask them, go through it, try to understand what the questions they are, and then try to organize yourself and put the answers in there. Now, it is also very important, and you will be allowed for this, to submit also a printed version of your exam. Most of the exam is actually going to be probably on Canvas, but sometimes you'll be asked to also present a printed version just in case for extra credit. So that's basically just to make sure if you went wrong, for example, in the solution, you don't lose all of the points that are associated with that question. At least you get some partial credit. Otherwise, I don't have anything to go by. I assume that you did the whole thing wrong and you get no markup whatsoever for that, no mark whatsoever for that for that specific question. So this is in a nutshell about the exam. We're not there yet. I think we still have about a week. We have about 10 days for that. I'm hoping to finish the chapter today. And then we have lab this afternoon. The lab is not going to be due as normally also labs are due, which is usually about a week after the lab. This lab is going to be given an extended period of time because I don't want you to be bothering too much with it because you have an exam. So the lab will be due actually on Saturday, okay? Few days after the exam. So hopefully after the exam, you focus back on the lab and you finish it and you submit it before it's too late. So this is in a nutshell where we stand in terms of all of the business. If you guys don't have any questions, so we're going to jump in and finish chapter 26, which is part of this exam. So let me share the screen. So this is chapter 26. We covered already 2 points from this chapter. We covered item number 1, namely what happened when we have resistors both in series and in parallel. And I made a table, I remember at the end last time, and I really want you to pay attention, close attention to that table, because that table will be enriched further when we discover another device called inductors. And I want you to also be mindful to the fact that capacitors and resistors, they add up differently when it comes to parallel and series circuits. And a lot of times, if you know these rules, it simplifies a little bit the calculations, it simplifies your life a lot. So it's a good idea to remember these rules. If not, if you don't want to remember them, just use the second thing, which was, I think, Kirchhoff's rules, to solve whatever circuit you have. If you have time basically with the algebra and you can manipulate multiple algebraic equations with a lot of variables, that's fine too. I mean, you can do that too. But the thing with it is that's probably an unavoidable thing anyway. So you might end up using Kirchhoff's rules to solve your system. So those are the 2 things that we covered last time. So let me quick reminder of what these things are before we jump, because we will need them. So the first thing is resistors in series. So when I have resistors R1 and R2 and ultimately R3 also, and so on and so forth, they amount as if to an equivalent resistor, which is simply the sum of all the resistors. That's it, okay? Where I is the index of a specific resistor. So add them up, okay? So this is as opposed to the rules when it comes to the capacitors. The capacitors had different rules when it comes to this one. They involve the reciprocal of the sum of the reciprocals and the reciprocal of that sum, basically, of reciprocals. This is exactly what happens. So this is the series. Resistors in parallel, though, they add up with the rule of the capacitors in series. So in here, parallel. So as if, again, I have the same resistors R1, R2, and so on and so forth. The equivalent capacitor, R equivalent, is the reciprocal 1 over, okay, the sum of all the reciprocals, okay? And the reason why I write it this way is because sometimes I have noticed is that we forget to take the last step. I mean, we add all of the reciprocals, 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 and so on and so forth. And then we find the sum algebraically, especially since I am punching it on the calculator. And at the end, I forget to take the inverse of that, okay? And that's disaster, that's a problem, okay? Because then the resistance will not be correct. First of all, it has the wrong units. It's not an ohm anymore, okay? So it doesn't work that way. So you have to take the reciprocal, and that is what that -1 in here, of the sum of the reciprocals, okay? So that's basically how you can remember. So this is basically the opposite again of what happened in the capacitors. In the capacitors, when they're in parallel, the equivalent capacitance is just the sum of the capacitances, no matter how many you have, okay? Just add them up. In this case, no, you add the reciprocals, and when you're done, you take the inverse of that, and now you have the equivalent resistance. It is very important to remember a property of this thing. If I have, for example, if I have a 10 ohm resistor, okay, and a 5 ohm resistor. In this case, in the case of the equivalent capacitance, the equivalent capacitor, the equivalent resistance, since I have resistors in here, when they are in parallel, is less than the smallest of which, so it should be less than 5. In other words, I have to take 1 over 5 plus 1 over 10 and take the inverse of that, and that should be, the common denominator is 10, I have 2 plus 10, and 2 plus 1, that's 3. So technically, this is 3 over 10 to the negative 1, which is 10 over 3. Okay? So when I take the inverse of all of that, I find 10 over 3. And 10 over 3 is less than the smallest of the resistors. So when you have a bunch of resistors and you put them on parallel to one another, practically, the equivalent resistance is that should be less than the smallest of all of the numbers in there. Whereas the sum, if they're in series, if this same two, namely they were in series, so I have a 10 ohm and a 5 ohm, the equivalent in this case is going to be more than the biggest of the two, the biggest resistance. So I look in here and I see that, for example, 10 is the highest resistance. When I calculate the equivalent capacitance, it's going to be higher than the highest one. Whereas in the case of the parallel, it's going to be less than the smallest of the bunch when they are in parallel. You see, this enriches your discussion when you're doing discussions toward the end. You're trying to see if it makes sense or not, and you look at the circuit, for example, and you find something that doesn't make sense. In a sense, for example, I have a bunch of resistors in parallel, and the smallest one, let's say, for example, is a 5, and you have 4 or 5 or 6 of them, and there is a 5, there is a 7, there is an 8, probably there is a 27 or something in there. So you know that the equivalent capacitance should be less than 5, yet your answer, for example, has a 6 or a 7 ohms in it. Okay? So you know there is something wrong. You know that you did something, there is something with the algebra, something did not work well. Okay? So this is something to help you. Does it make sense? It doesn't mean that if you find less than 5 that you're right, but it means that you were not wrong, in the sense that there is a clear distinction in here about being not wrong and being right. Okay, so I want you to, when you're doing the discussions, to remember these things. Try to remember it. For example, if you have a bunch of resistance and they are all happen to be in series, one hiding behind the other one, and a bunch of them that were in parallel, and now you connected them, and they became basically, now you basically added them up, and now they became in series with something else, and you notice that, for example, one of them was 27 ohms, and your answer at the end was, let's say, for example, 20 ohms. So you know that there is something wrong also. It should be bigger than the biggest of the bunch, okay? So this is some of the things I need to bring your attention to when you're connecting and playing actually with the actual devices themselves. You need to be mindful of this effect. If you have a specific voltage, for example, if you have a specific tolerance, for example, on your multimeter, or I'm sorry, on your device, you don't want to exceed it or go below it. Let's say, for example, the multimeter is set up to maximum 10 volts, for example, on it. Or let's say, for example, a maximum of 10 amps, for example. And by mistake, you connect the resistors, for example, in such a way you generate 15 amps in the circuit. Well, then you're damaging the fuse on the multimeter probably will blow. So you have to be very careful in that. So you have to be very mindful of what's going on in here. So before you actually add up things, so you know roughly where you're headed before you actually put things in circuit, and then now the voltmeter or the Ohmmeter is not working anymore, and we have to call somebody to come and replace the fuse in it. So that's basically some of the things. Of course, it could have far more damaging things than just a fuse. So that's basically some of the things that you have to be mindful of. So this is basically in a practical sense of what you do when you're discussing solutions, some of the things that you might be looking for. There are a lot of things, okay, and depending on the context. But this is some of the things, at least when it comes to resistors, that you need to be watchful for. You need to have a clear understanding of. Now, we have also discussed Kirchhoff's rules, and there are actually two basic rules. Two basic rules are the following. One, In the node, which is basically when a bunch of wires meet together, the sum of all the incoming and all the outgoing of the current, with a convention of one of them is being positive and the other one is negative, the convention can be yours. It doesn't matter which one, okay? You have complete choice. Must be the same, meaning that the sum of the currents are 0. That has to do with the conservation of charge. That means if 10 coulombs come in 1 second, 10 coulombs must leave in 1 second. So this is the rule of the node, or the junction rule has to do with the conservation of charge. The second rule has to do with the loop. So if you have a loop of some sort in here, if a bunch of devices connected to one another, it doesn't matter what they are, okay? And your starting point is your ending point. And you go in a loop, again, you have choices. Either you go clockwise or counterclockwise. Same thing as you had choices in here of determining which one is positive and which one is negative. You have also choice in here which way you circulate the loop, clockwise or counterclockwise. At the end, the voltage drop, and the key word in here is drop, okay? The voltage drop is equal to 0. That is, again, conservation of energy, because the voltage drop times Q is actually the amount of energy. Somebody is keeping track of the height, and you go around the circle and come back. And again, at the end now, that since you went, doesn't matter how many times you went and how many floors you went down and how many floors you went up. If your starting floor is your ending floor in terms of height, you gain no height. You might end up in a different apartment of the same building, but height-wise, you didn't gain any height, you didn't lose any height, so you're in the same level. That is the same thing, because actually height is a gravitational energy. Same thing in here. The potential is actually the electrostatic energy in this case. So that is actually another expression of saying that the energy is conserved. So these are the two rules, the junction rule and the loop rule. In both of them, you have choice. Now, I had given the example last time when we met of that specific example. And again, we found usually there is one too many junctions. One too many junctions. This is a general note. You will always end up with one too many. So if you have 5 junctions, know that you actually will only be working with 4. Okay, the 5th one is a combination of the previous 4. Which 5th it is, it doesn't matter. You have complete choice. It could be the first one, it could be the second one. One of them is no more than just a restatement of the others, combination of the other, linear combination of the previous ones. And then also, you will have always one too many loops. That is actually another one too, as far as loops. So if you have 5 loops again in the circuit, understand that one of them is just a linear combination of the previous 4, okay? So that's also another. So again, now, since I'm solving problems involving electricity and I'm doing resistors and capacitors and things like that, by the way, these 2 rules in terms of junctions and loops, they work also for capacitors. And actually also any device, as a matter of fact, anything that you have in a circuit. So at the end, in order to generate something interesting in my discussion toward the end, is that after I solve the entire problem, pick the junction I did not pick before, and add up the currents in there. I should find 0, taking into account the convention that some of them are positive and some of them are negative. Or if you wish, if you don't want to express it that way, you could say, okay, all the incoming currents must be equal to all of the outgoing currents, okay? And add up the right hand. You end, for example, with 7.23 amps. Add up the left-hand side, and you should find 7.23 amps, okay? You should find the same sum, okay? Could have, for example, 5 plus 2.23, and the other side is 4 plus 3.23, and at the end, both of them add up to the same number. You understand? So this is another way, excuse me, of checking. Another way of generating an interesting discussion. Does it make sense? It does. Because if I find the same, now if I don't, then there is something flawed in here. that means I made somewhere a mistake, okay? I need to go back and try to correct it. Same thing with the loops. Take the loop I did not count for and add up the voltage drops from end to end. Okay, again, I want to go back to this word in here because it's important. This is the drops, the drop in voltage. So if I happen to go through a battery, I have to be very careful. If the battery is this way, and I'm going that way, this is positive and negative, the drop in here is going to be minus epsilon. Because this is the actual drop, it should be the other way. So this is a rise, actually. So my way of saying I'm rising, I'm dropping by negative epsilon. So you have to pay attention to this word in here. Same thing with my resistors. If this is the resistor, and if my current is flowing this way, well, I thought so. This is my assumption. I'm thinking the current will flow this way. Then if I go this one, this is actually, I'm dropping with an Ri. Whereas if I'm doing it in the opposite direction, I'm dropping with a minus Ri. You guys understand? So if I'm just following the current, the drop is actually Ri. If I'm opposite to current, then in this case, I am actually dropping with a minus Ri. So I could do the same thing, for example, and I happen to hit this resistor where the current is flowing this way, coming down on it. So in this case, the drop in here is minus Ri. In other words, I'm rising. This point is a higher potential than this point. So this is a higher than this point, which is lower. Okay? So if I happen to have come from low to high, then I can say, okay, I'm dropping, because the word in here is drop. I'm dropping by minus Ri. In other words, I'm rising. I'm going from low to high. Okay? Same thing with the capacitance. I have to be very careful when I'm applying this rule. If I happen to think that this is where the positive charge is, and this is where the negative charge is, and if I happen to hit this capacitance this way first, okay? This is an actual drop from positive to negative. So again, in this case, I'm saying in here, the drop is going to be Q over C, okay? That's how much I'm dropping in voltage. But if I'm hitting it in the opposite direction, from low to high, then similar to the battery, if I'm going this way, and this is still positive Q and this is still negative Q, then in this case, I'm actually dropping by negative Q over C. Okay? Assuming that there is a current in here that is flowing in the circuit. Doesn't matter in here for the capacitor. As long as there is a charge, there is a drop in potential, period. End of story. The only thing in here, the word drop, since this rule in here says drops, sometimes I actually am rising, so I have to make sure that I'm dropping with a negative number to reflect that. In other words, this battery, if I happen to go and hit it in the opposite direction, then in this case, I'm actually dropping with an EMF epsilon. So if that's the case, then this is the drop. Again, these things, first of all, take practice. Once you practice them long enough, I think you should be able to be good with it. But the point in here is you have to remember these things in here. You always ask yourself, if I am in a resistor and I am going around and happen to go in the same direction where the current I chose to be, then in this case, hey, that's a drop. If I'm going in the opposite direction where the current is, then I'm actually rising. Now here is another detail that can throw you off big time, okay? You really have to remember this last point. What happens if I assign current, and this happens a lot, especially if I have two batteries in the system. One of them is 24 volt EMF, and another one, for example, is 16 volt EMF, okay? And they are situated in different resistors. My thinking is that the 24 will push more current. So if both of them happen to be in the same direction and they are in the same side, then I can think, okay, the 16 plus the 24, I actually have an equivalent battery of about 40 volts. But what if there is another junction somewhere and one of them is pushing this way and the other one is this way, and then there is a resistor in here, a big resistor in front of the 24, whereas there is a small resistor in front of the 16, and I have no clue. I have no idea based on these numbers in here. So what would I do? Here is the thing. When you're building your circuit, don't worry about that detail. Just assign direction for current. any direction, okay? And follow your rules. As long as you said the direction of the current is going this way, and I hit a node, and that current splits two ways, and you give them directions, and you hit another node, and that current splits in another direction, one of the ones that split from the first one, and then when they meet back again, they're going to go back to the same current, and I calculate. If the signs of my currents turn out to be all positive, then hey, my choice of the directions were perfect, were good. I was lucky. If one of them is negative, or all of them happen to be negative, that is fine, okay? That means my choice of the directions for that specific current or for all of them were wrong. In other words, as a matter of fact, there was a huge drop probably in potential next to that big resistor that basically by the time the current gets on the other side or something or whatever happened in here, in this junction, that the current that was pushed by the 24 at the end ended up being overwhelmed by the 16. Now the 16 is actually that is dominating on the other side, okay? So that's basically how you can look at it. And maybe there is a capacitor that was draining energy from this battery now that nullified it basically after a while. Now the other one is actually the one doing the work. So this is some of the rules, the things that you need to look for when you're doing your problems. So again, take a direction and solve, okay? If the signs work out for you the way that you had them, all positive, that means you had chosen the correct direction everywhere. If the signs happen to be now, some of them are not correct, all you have to do is just say, for example, that, oh, the current actually was flowing in the opposite direction, and check the junction rules now and check everything else and make sure that the voltage drops work now with the correct sign, and everything should be fine. And if you want to, you don't have to, go back to that specific current and change its direction and redo the calculation, and now it's going to pop up as a positive number all over again, okay? That's simple as that. You don't have to do that last step, but if you want to, you can just go and change the direction for that and redo the whole calculation from the beginning, and you should find that current and everything else to be positive now. So these are some of the ideas that you will encounter when you're solving problems. So I'm hoping that, again, you will not really understand these things as much unless you actually do them, unless you actually go and do those problems and all of the things, so that now you will encounter those situations and you will understand them better. So those are the 2 points from the discussion we had last time. We spent almost half an hour talking about them, which is fine. The discussion in terms of the multimeters in general really need to be deferred to later on when we discuss magnetism, because here is the reason why. In a multimeter, which is necessary, by the way, because now we're talking currents, we're talking voltages, we're talking resistors, we're talking all of these things. We really need to understand how do we measure these things. I mean, if somebody tells you how do you measure the force, you're going to tell them take a spring, scale it. If it's stretched with this much, then it's this much force. Now use it to measure forces. So that's basically how you can measure forces. Use the same spring to measure accelerations. As a matter of fact, that's how you measure masses too, using spring. The scale, it works only on Earth. So it happened to be in interstellar space. How can you measure masses? It's actually with a spring, okay? So the same thing in here. How do we measure currents? Well, currents, you have to think about it this way. You have a magnet. And again, that's part of the next few chapters, okay? So you have a bar magnet in here, and the bar magnet sitting by itself, and you have a core, an iron core, okay? And you wrap around it a coil, okay? That coil is wrapped, okay? So it's one coil, not too many, okay? It's wrapped around, okay? And usually you have a spring in here to bring it back to an equilibrium position, okay? To a zero position. So while there is no current in it, it's sitting at zero. Now you run a current. Remember, this is a magnet. There is a north pole in here and there is a south pole in here somewhere, okay? So there is a magnetic field in here present, okay? Between these ends. Now, once the current starts to go through, basically once you use this to measure currents, okay? This wire in here has specific resistance. So the resistance of the coil is known. So you can test that, you can measure that, or you can make it at the standard, so, or calculate it, doesn't matter. So the resistance is known. So resistance of the coil is known. Now you run a current through the wire. Because now there is a wire looped around this core, this iron core in here. The iron core, now since there is a current running through it, it's going to create its own magnetic field. Or if you wish, it will have a magnetic moment by itself, okay? That magnetic moment is actually amplified, made more stronger with the presence of the iron core. So the iron core in this case plays the same role as the dielectrics plays when you place it in between the plates of the capacitor. It makes the electric field stronger there. Or same thing, this one actually makes the magnetic moment of that iron coil even higher, which makes this interaction between the magnetic field and the magnetic moment of the core higher and higher, which means this needle will move one way or the other depending on the direction of the current. If, for example, the current is going clockwise, let's say, for example, it moves this way. If the current is moving negative, the opposite direction is going to move the other way. So now, because there is a torque now, okay? And the torque is actually resulting between the magnetic moment and the magnetic field. And we will see that later on. The torque, actually, we can write it, symbolically as mu cross B, where B is the magnetic field and mu is actually the magnetic moment. Again, this discussion should happen down the road when we do chapter 27 and 28 and 29. But I'm just giving you an indication of how this works, okay? Now, this torque will turn the whole thing, the whole apparatus. Now, how much it turns depends on how much current is flowing in it. If it's a weak current, there will be small magnetic moment. If the current is higher, there will be higher and higher magnetic moment, up to a maximum value, okay? Obviously, if I cut the current, then there is no mu now anymore, so tau is 0, and the spring will bring it back to the equilibrium position, okay? The spiral spring will bring it back to the equilibrium position. If I move the current in the opposite direction, mu will have a negative direction, and the whole thing will spin in the opposite direction. Then again, if I cancel current, that's going to go away. So now that's basically how we measure currents. So there is a coil in the galvanometer that makes it spin one way or the other. But the maximum current I can measure depends, of course, on this internal resistance, and that's it, okay? Let's say, for example, this is supposed to measure milliamps, so that's all it's going to go for me. And if there is an internal resistance of 20 ohms, so that's all it's going to do for me. So what I do in this case, I make it, and if I want to measure, for example, an amp, for example, or something else, so how much resistance I need to do, so what I do, I take in here my ammeter, which is really a resistance and a current running through it, which is maximized in this case to a milliamp, and I place it in parallel with another resistor, and then force the current to stay 1 milliamp in the actual this division. Now I need what is called the shunt resistor, and that one is the one that needs to be there so that it can, the whole current that comes in here now is an actual amp. So there is an amp in here. Part of it, a milliamp, will go through the actual coil to spin it, and the remainder, which is 0.999, if you wish, amps, will go through the rest of the shunt resistor. How much this resistance need to be should be a very simple calculation in this case. Because again, the entire apparatus in here, I know that the voltage then across these 2 points is the same. The voltage across this one is just simply 20 amps times this maximum current, which is a milliamp, okay? And I need to measure 1 amp, so I know that this is 1 amp minus 0.001, so this is a 0.999 amps times the resistance in here in the shunt. So in this case, all I have to do is equate these two numbers, and that gives me how much resistance I need to place there. Just divide these two numbers and you're done. So I can use the same device to measure different resistance by just basically changing the tolerance on it, okay? Changing the dial on it, okay? If I want a milliamp, I do this one. If I want a hundredth of an amp, I do this one. If I want a tenth of an amp, I do this one. If I want an amp, I do this one, and so on and so forth. And that's exactly what I do. I change the dials, or there are actually where I place, so there is a common port in here, and where I place the others, it's labeled actually on it, and where I put it is actually the starting. Technically, usually it's a good idea to start with the highest amp, and then you work your way down, if you don't know the current in the circuit. You don't know if it's 1 amp or probably a milliamp or something. You have no idea in the circuit, so up front you don't know. So what you do in this case, you start with the highest value and see if the needle moves. If it doesn't move, that means the current is a lot weaker than that, okay? So you move it to the next one, and you see if the needle moves at all. If it doesn't move, that means it's still weaker than that. And then you move it to the last point, and now you should see it. So the current actually is probably 0, maybe it's a 5 milliamp. That's why when you had it in the amp, 5 amp you don't see noticeable motion at all in the needle. So that's why you have to move your way down that way. Now, if by mistake, you start with the smallest value, a milliamp, for example. And when you put it in, the current is probably already 12 amp in the circuit. So in this case, what happened to this ammeter is gone. The fuse is blown, okay? Because it went way above its tolerance. So there is so you run the whole current in there through this whole thing, the 12 amps, whereas this one can maximum tolerate is 1 amp. The wire is not that thick to support that much current in it. So it's going to blow away, or there is a fuse that usually prevents that from happening, and that fuse actually blows away, and now you're going to go and ask a technician to replace the fuse, please, okay? So that's basically what the ammeter is. Now for the voltmeter, it's similar, except you put things in series. You don't put them in parallel, okay? And the series now, so you take the same device actually that you used as an ammeter, but you put it as a so now you have your R of the coil itself, and this is again at most is 1 milliamp, and you would want it again to be in series with different devices. So there is in here, there is a switch, and that switch will put it either with this one, with this resistor, or with this resistor, or with this resistor, depending again on which voltage you would want to measure, okay? Now you're not measuring current anymore, okay? The current at the end in this case has to be 1 milliamp. But now, this resistance, which is now the resistance that you need to make it happen, has to be high enough to bring down whatever current in here that you have going in here, small enough so that it's 1 milliamp, okay? So again, this is a voltmeter, and the voltmeter has to be placed in parallel with the actual device that you're measuring your, whatever you're trying to measure the voltage across into. So now when you put it in here, let's say, for example, the current that's, oops, I'm sorry. The current that starts from one end is high enough, small percentage of it is actually going through the circuit in here, through the voltmeter itself. But again, you need this resistance, or even this one or that one, very high in order to only allow 1 milliamp. Most of the current will actually flow through the device. So this one, you need to place it in parallel, whereas this one in here, you actually need to place it in series with the circuit. So if you're trying to measure the current flowing through this resistor, then in this case, you place it in series. So let's say, for example, 1 amp, it's still 1 amp coming through the ammeter, but it's going to be measured by the ammeter in here, depending on the tolerance. The voltmeter has to be in parallel. So this is in a nutshell how this device works. Usually it's a multimeter that measures both of them, okay? And with the dial, you change the location for it, okay? If you have had a chance to look at the multimeter, that's basically how they have their forms in. Now, an ohmmeter is similar, except an ohmmeter in this case, you have to use Ohm's law. Basically, the same device is used using Ohm's law that generates its current, and the current now is used to find, it's scaled actually with the resistance. And there is a potentiometer, which is actually a combination of this device and actually a well-known resistance. I'm sorry, you move the resistance in such a way to cancel the current. When the current is now coming 0, then you can scale it so that you can read the batteries. Actually, honestly, to understand better what's going on, the physics behind it, all you have to do really is I mean, you have to have an understanding of what that expression is, I mentioned before, and we will talk about this one more down the road. So, the summary of this is the following. For an ammeter, which could be have different names, galvanometer, depending on the current that it runs to, it has to be in series. Okay? And whatever you read in here is the current I. That is running through this device, whatever device that you have it connected to. Okay? For a voltmeter, you connect it in parallel. So the voltmeter now will read whatever voltage is in there. Okay? So that's basically in a nutshell how these devices work. So if you read in here 10 volts, that means the voltage across this resistor is actually 10 volts. So that's basically how this summarizes to, okay? So from now on, we're assuming that we have ammeters and voltmeters, and that's all we need right now to be working with our circuits. If we were in the lab, we'll use this to basically do measurements for voltages, currents, and actually ohmmeters also to measure the ohms. And when we're doing the ohms, we don't connect them with a power source. For this one, you really need a power source in here. So you need a battery of some sort at some point in here, okay? And you need a battery in here to measure this one. But if we're measuring the battery itself as a potentiometer, or if we're measuring the resistance, then in this case we don't need this. For the battery, of course, we have to have a battery to measure how much its EMF is. For the resistance, no, we don't need that. Okay. So that's basically in a nutshell what these things are. Any questions so far? This is just a discussion. Okay. In other words, it will have very little implications for your homework things, okay? Assume that you have devices, but it's interesting. We have to really keep in mind that it's not physics unless we measure it, and you need to know what measuring devices you have, how to measure things, okay? Otherwise, we're doing math. Any questions? Because what comes next is we're going to turn on the gears a little bit. So you need to get all of your calculus, the money you spent on it, you need to earn it now. You need to, actually not, honestly, it's not that complicated, okay? I'm just, this is the first step, okay? It's simple integral. Okay. So charging a capacitor. Okay, so this is the RC circuit. So imagine with me the following circuit. I already mentioned it last time. So we have a battery. We have a switch. It's actually a three-way switch. An AB switch. This point is A. This point is B. Oh man, sometimes this thing doesn't work. And I have a resistor, R. I have a capacitor, C. And the whole circuit usually is connected to a switch, okay? For safety measures, usually, no, there is the switch there. We don't need anything else. So the switch can be in an off position, meaning that it's neither in A nor in B, okay? Like right now. So this is what we're gonna do. We're going to assume, and again, you have choices in here, that at t equal to 0, there was no current in the circuit, I equal to 0, okay? And Q is equal to 0. Okay, Q equal to 0 is not an issue. We could have Q naught. We could have an initial charge in the circuit. But to make it a little easier, so we're gonna assume that there was no charge. This is initially, this is at t equal to 0. Okay, and then of course we have the EMF, and the switch was in not in the off position. It was not in A or B. Okay, now at t equal to 0, we're going to move the switch to position A with this initial conditions. T equal to 0, we're going to put switch in A. In that process, what happened, let's talk what happened, at least in terms of the physics. Now, we have an EMF. It's going to see positive charges in here and negative charges in here. So it's going to see current starts to flow from the positive side, since this is closed now, goes through the resistor. So the current is going to come in here and build up a charge from this side. Of course, a negative equal amount of charge starts to deplete from the other end and follow the same current I to the battery. So a current I, now there is a charge that starts to pile up in the capacitor. So there is a buildup of a charge, okay? Now, at some time in the future, not at equal to 0, at any later time in the future, there will be a current already flowing through this resistor. So there is a voltage drop in this direction, Ri. And there is a voltage drop in this direction, which is Q over C. This is a C, by the way. Q divided by the letter C, okay? And of course, there is no other voltage because we're assuming the wires are ideal. They don't have any resistance whatsoever, okay? Now, this will continue pushing the current, but there is a voltage that starts to grow because the charges are accumulating now through the capacitor. And because the charges are accumulating through the capacitors, they don't allow more and more charges actually to come in there. So there will be resistance to this pileup. So the current actually starts to go down because the battery cannot push more and more current, because now there is a resistance from this one. At some point, this capacitor will be fully charged, and we'll have an EMF equal in might and power to that of the battery, in which case it's going to kill the current. There will be no more current in the circuit. So if you wait long enough, and this is critical for your problems in the exam, if you wait long enough, there will be no current flowing through the capacitor. So the capacitor will be an open circuit. So as if it's a switch that you just opened it, okay? Because now it has built a lot of charges in it. So let's try find the mathematical expression to what's going on in here. So we're assuming now, of course, this time has to be t equal to infinity. So when this situation happens is when time is an infinite amount of time, if we wait long enough, okay? If not, we're in transition somewhere in between them. So at a finite time t, after we put the switch in position A, there is a finite current in the resistor, okay? So now I can apply Kirchhoff's rule. I have, because remember, this B is not part of the circuit, I only have one loop, and I'm going to go clockwise on it. And I take a point in here immediately above the battery. There is no resistance in here whatsoever, no voltage drop. The minute I hit the resistor, I have a voltage drop. And I know exactly what that voltage drop is. It's Ri, because I'm in the same direction as the current. So the voltage drop across the resistor is Ri, okay? Then, after I leave the resistor, there is another voltage drop, Q over C, in the capacitor. So there is plus Q over C. The minute I come across the battery, I'm going in the opposite direction. I'm going from the anode to the cathode. And then in this case, actually, it's a rise. So it's a drop by negative epsilon. After I leave the battery, I am back to where I started from, and I closed my loop. So in this case, it's equal to 0. Okay? So this is Kirchhoff's rule. Now, the current and the charge are related to one another. Remember, the current is the rate at which the charge is piling up in the capacitor. This is how we define current, actually, to begin with. So the current I is dq over dt. So I'm going to take that expression and plug it back into the first equation. So now I have a time-dependent equation. I have actually something that I have never seen in my life before, namely R dq over dt plus Q over C, I'm going to take that epsilon to the other side. I'm going to move it to the other side. So it's going to now have a positive sign. Okay? This is actually a differential equation. Okay? Fortunately, we don't really have to take d phi q to solve it because it's not hard to do. All I'm going to do is move this term to the other side, meaning its sign will change now, and reorder my expression so that it becomes just an integral for me to do. So I'm going to say R dq over dt is equal to the EMF minus Q over C. Remember, when I take it to the other side, the sign changes. So I'm going to take the common denominator, which is actually C, and multiply epsilon by C. And now I will have an expression that looks like this. C epsilon minus Q over C. Basically, I just use the common denominator. Furthermore, I don't like Q to be by itself in here. I'm going to move it to the other side. In other words, I'm going to multiply by -1. So minus Q minus C epsilon over C. It's the same thing. I'm just trying to manipulate my expression to make it look like an expression that is familiar so that I can do the integration. So this is how the expression at the end of the day look like. R dq over dt equal to minus Q minus C epsilon over C, okay? Now, I'm going to take a change of variable. I'm going to change my variable because this Q minus C epsilon, remember C is constant, is the capacitance, and epsilon is that of the EMF of the battery, so that's also constant. If it's 12-volt battery, it's 12-volt battery. So these two numbers are constant, so I'm going to assume a new variable in here, which I'm going to call Q prime, not derivative, okay? It's Q prime, just another Q, which is equal to Q minus C epsilon, okay? Then in this case, from this expression here, because Q depends on time, so is Q prime. So the derivative of Q prime over T is equal to the derivative of Q over T, because this is a constant. The derivative of a constant is 0. Let me write it 0, okay, just to make sure that I took the derivative of a constant, okay? So having said that, I sub the value of dq over dt, which is dq prime over dt. So I write the first expression R dq prime over dt equal to minus q prime now over C. So the advantage of doing this transformation in here, namely putting q prime equals to q minus C epsilon, is just to get rid of that term in there and combine it with my expression in here. So now I have this expression, which should be easy enough to do. So what I'm going to do is I'm going to move the q prime to this side and then move the t dt to the other side. So I'm going to swap their places, and the expression looks like now R dq prime over q prime equals to minus dt over C. We are almost there, okay? Again, we're going to move R to the other side by dividing by R, if you wish, so that I have a familiar expression to integrate. So dq prime over q prime is equal to minus dt over RC. Now I integrate. This is an indefinite integral. This is just a just try to find the antiderivatives. That's all. This is stuff that you should have done way back in Calc 2 or Calc 1 or something. So the integral of dq prime over q prime. Any idea? The integral of dx over x. Any suggestion what that might be? That's a discussion for today. What is the integral of this term? In other words, what is dx over x? What is that integral? Because q prime is just a dummy variable in this case. Come on, guys. You took calc already. Come on. Okay. Does everybody agree with Israel, or is he wrong again? Okay, Faraz agrees with you. I think you're right. Okay. I think he's right. I think it's the log 2. Okay. Anybody else objects on it? Anyone objects on it, I should say, not anyone else. No? So this is ln. Actually, I should really put it in parentheses to be more specific, okay? This is ln of q prime, okay? And I'm gonna put the constants on the other side if you don't mind, okay? And the integral of dt now, the integral of dx, because r and c are constant. The integral of dx. Come on, there should be more than these two guys in here. So I'm looking for the integral of this term now, because remember, RC are constant. So basically, I'm looking for the integral of dt, okay? Or if you wish, since it's a dummy variable, the integral of dx. This is as simple as it gets. It cannot get any simpler than this. Okay, very good. Thank you for us. Anybody else second him? Okay, thank you, Heather. Okay, very good. So basically, it's minus t in this case over RC. But to follow the advice of Israel, we have to really add a constant. We can't really live without it. Okay, RC. So if we didn't add it in that side, we have to add the constants in here. So I'm going to call it constant because I already have a C in the problem. Okay, I have already the capacitance C. So it's not a good idea to use the word C again in this case. So I'll probably call it an A. How is that? Plus A, where A is a constant. Okay. So now it's just a matter of taking this ln and make it into an exponential. So if I take the exponential of both sides, this simply becomes q prime, and this becomes the exponential of this term and that term. So it's the exponential of a times the exponential of negative t over RC. Because this is part of the properties of the exponentiation. The exponential of the sum is just the product of the exponentiation. So this is another constant. The exponential of a constant is going to be a constant. So I'm going to call it B now. Whatever constant that is, okay? I don't want to call it C because, again, we have a C already in the problem and it might be confusing. Let me go back into my original expression for Q prime. Remember, Q prime was equal to Q minus C epsilon. And I really have to find Q, not Q prime. So Q prime, which is Q minus C epsilon, is equal to a constant, which now I'm calling B, equals to minus T over RC. Okay? So in other words, Q is a function of time. Is simply C epsilon, when I move it to the other side, plus B times exponential of minus T over RC. Let's go back to at T equal to 0. What happened? How much charge did we have in capacitor? At T equal to 0, there was no charge in the capacitor. This is when the switch moved to the position A, okay? Again, we have an A and B in here for the switch. Hopefully that these constants don't get confused with those two, okay? So at T equal to 0, Q sub 0 was 0. So that means C epsilon plus B exponential of 0, and exponential of 0 is 1. So this number is just 1. Must be equal to 0. The whole thing is 0 when you add them up. So that means C epsilon plus B is equal to 0. That means B is equal to minus C epsilon. So from here, the expression for the charge then, Q in the capacitor at any time in the future is equal to C epsilon. I took it already as a common factor, minus times 1 minus epsilon of, E to the power T over RC. Okay? So this is the expression that tells me how the charge is piling up in the capacitor. Okay? If I want to find the current I sub t, remember, is equal to the derivative of this expression with respect to time. The derivative of 1 is 0. The derivative of exponential negative t over RC is negative 1 over RC times the exponential itself, because the derivative of the exponential is the exponential. But don't forget, you have a coefficient in here to the derivative, to the term you're taking the derivative with. So this whole thing becomes C epsilon times negative 1, this negative 1, times the negative 1 over RC times the exponential itself, e to the negative T over RC. Okay? The negative and the negative become positive, and the C cancels the C, and at the end, the expression for the current, I, will simply be equal to the EMF over R times the exponential of minus T over RC. So these are the two expressions I find for the current in the circuit. So indeed, what happened at t equal to infinity? What happened when time goes to forever and ever and ever? This current indeed goes to 0. When t goes to infinity, exponential of negative infinity is 0. Okay? So the current I tend to go to 0. What happened to the charge in the capacitor when t goes to infinity? So when t, we wait forever, basically, is going to be, the exponential is 0, but 1 minus 0 is definitely 1, so Q tend to go to C epsilon. So let's see what's happening here. So if we wait long enough, the current will be 0 in the circuit, which is what we thought will happen, because we thought that this problem becomes worse as the charge is piling up in the capacitor, which tend to resist the EMF. As a matter of fact, it will have a charge C epsilon in it. How much voltage that is? It's the charge over C. So cancel the C. It would have exactly an epsilon, the EMF. So the voltage drop across the capacitor will be that of the battery. So in other words, the capacitor builds up charges in it, and the voltage drop in it will be the same one that is where the battery is. In other words, it's going to oppose it, because a positive sign in here and the positive sign in here, and they will work against one another. Since both of them have the same voltage, they cannot, they are basically looking to one another. Initially, it did not have charge, so the battery was able to push current through it, so there is no problem. But as the charge starts to pile up, it had built enough potential, which is the EMF, to counterbalance the battery in this case. So they are not going, no more current. As a matter of fact, I equal to 0, that is expected now, because as if you have two batteries, both of them have the same EMF, and you connected them positive to positive, and both of them trying to push current against the other, and they cannot, because both of them have the same energy. So in this case, they cannot do anything, so there will be no current in the circuit. Obviously, if you put them in the opposite direction, where negative is connected to positive, then in this case, hey, there will be a huge current flowing through the circuit. Okay, so you need at least a big resistance there to dampen things. Okay, so this is basically what happened in the circuit. Let's look at it graphically. Okay, graphically, the exponential growth is like this. So at t equal to 0, there is no. So I'm looking at Q now on the capacitor. Okay. And as time flows by, it's going to get closer and closer from the maximum value, which is C epsilon, okay? And it's going to get there exponentially. The same thing for the current now, which is actually the voltage across the resistor, is going to start to decrease from an initial value at t equal to 0. Let's look at t equal to 0, what happened? When t equal to 0, the current is epsilon over R, because the exponential of 0 is 1. So this current, when t equal to 0, is actually 1 times epsilon over r. So initially, the current will be epsilon over r. And it starts to decrease exponentially. Okay? If I want to know how much voltage was there across the resistor, well, all I have to do is multiply the resistor times the current, and the current initially is epsilon over r. So how much current at t equal to 0, how much voltage drop at t equal to 0? Well, all of it is actually in the resistor. So initially, the current is epsilon over r, and if I multiply it by r, so all of the voltage drop actually was in the resistor. So at t equal to 0, when I immediately put the switch on position A, all the voltage drop is actually across the resistor. And there is no voltage drop across the capacitor, because at that time there was no charge, okay? And as the current starts to pile up charges on the capacitor, there is a buildup of potential now across the capacitor. And if I wait an infinite amount of time, that drop in potential will be exactly that of the EMF, and now there will be no current running in the circuit, meaning that there is no voltage drop in the resistor. So initially it's all in the resistor, at the end it's all in the capacitor. So that's basically how you build charge in the capacitor, okay? This is not a complete story though. It never ends until you actually do the energy. So my question in here is, how much did we put energy in the capacitor? It's very easy, okay? Just take the charge and divide it, square it. So the energy, after an infinite amount of time, you wait forever, like I said, is going to be the charge when t goes to infinity divided by 2c. This is squared, by the way, okay? And I know what that is. It's just, the expression is c epsilon, but don't forget you square it, because that's the limit of the charge after an infinite amount of time is c epsilon. You square that number, and now you have the charge in there. So this is simply equal to 1 over 2 c epsilon squared, okay? So that's how much energy we put actually from in the capacitor. Where did we get this energy from? That's the second point of discussion. Where do we get the energy from in this RC circuit? Any idea? At the end of the day, we have a charge of c epsilon in the capacitor. So we calculate the energy is simply the charge squared divided by 2c. And we can find a number for it. So there is no problem with it. My question in here is, where do we get the energy from? Any idea? Here are two choices, okay? You guys hopefully don't think that the switch has any role with it. It's either the resistor or the battery. Where do we get the energy from? Resistor or battery? Okay, thank you, Faraz. Thank you, Alexander. So basically, it has to be the battery. It cannot be the resistor. If anything, the resistor has a negative role actually in the circuit. So let's see how much energy we took from the actual battery. So again, this is the energy now stored in the capacitor. It's 1/2 of c epsilon squared. Now, how much energy we drained from the battery? Now, battery. So this is energy drained, because the whole thing must have taken energy from the battery. So in this case, it's very easy to think about it. The whole process took an infinite amount of time. So what I'm going to do is sum the power from 0 to infinity, because that's when we turn the switch of the power as a function of time, okay? And the power across the battery is simply P on the battery is the EMF times the current. That's what we have seen way back, I think, from last chapter. The voltage times the current. That should give me the power. The voltage is a constant number, so we don't have to worry about it. It's the current that I have to integrate. So the U in the battery then, this is how much energy we took from it, is the integral of the EMF times the current. The current, and the integral has to be from 0 to infinity, because I really have to sum all of this from the beginning of the process when I turn the switch to position A until, and wait forever. So the expression for the current, it's actually this area. This is what we're looking for, okay? So this is the expression that I have to integrate, okay? So again, the EMF over, this is the current, the EMF over R times the exponential of negative T over RC. The whole thing is integrated over dt. Again, the EMF times the EMF is EMF squared divided by R. And that's the integral from 0 to infinity of exponential of negative T over RC dt. Okay, if I integrate, I have to divide by negative 1 over RC. So that means I have to multiply by negative RC, okay? And then the integrator of the exponential is the exponential itself. So this should be easy enough. So the first thing in here is minus RC times exponential squared over R. The integral from 0 to infinity now is just going to be the exponential of negative T over RC from 0 to infinity. Okay. At infinity, the exponential is 0. At 0, the exponential is 1. So what to happen in this case is, first of all, there is a cancellation here between the R and the R. What happened in this case is negative C times epsilon squared times the upper limit is 0 and the lower limit is 1. And 0 minus 1 is negative 1 times the negative, which is good because we should not find a negative energy. That's a problem. So we found a positive value, which is C times epsilon squared. So this is how much energy we took from the battery. This is how much we took from it. This is how many joules we took from it. Let's say, for example, we stored 10 joules, but 10 joules is just half that number. So that means we took 20 joules from the actual battery. Okay? So this is twice as much. So we took twice as much to store half of it. You guys understand the story now? So we took from the battery C times epsilon squared Let me go back to the circuit. Okay, I'm trying to find. So this is how much energy we drained from the circuit. We drained C times, let me get another tool in here, another one. C times epsilon squared. Half of it now, after an infinite amount of time, is now stored in here, 1/2 of C epsilon squared. So we have lost energy in the process. That's the third question of the day today. Okay, where did we lose that energy? We took C epsilon squared from the battery. 1/2 of C epsilon squared we know now is stored in the capacitor after we wait a long time and we charge it by an amount that is C epsilon. The question is for you guys, where do you think the energy is lost? Come on, there is only one culprit left now. There is only one. Yeah, it must be. Cannot be anything else, since the switch has basically no role in the whole process. So the resistor is the one where the whole thing is went kaput, where we lost energy. And I know exactly how much I lost, because if I took C epsilon squared, I must have also stored 1/2 of that. That means half has gone there to the resistor. Okay. So half the energy must be lost in the resistor. So here is the story in a nutshell. C epsilon squared taken from the battery. 1/2 of that is stored in the capacitor. So the question is, 1/2 of C epsilon squared must have gone to the resistor. We need to check that. We can't really take anybody's word for it. So what we should do now, okay? We know the power in the resistor is equal to Ri squared, okay? So all I have to do is do the same trick as I did for the resistor, for the battery, except now I have to integrate this expression. So now, how much we lost is equal to the integral from 0 to infinity of Ri squared dt. Whereas I squared, I itself is given by that exponential, namely epsilon over R times the exponential. So I have to square that. So it's going to be an epsilon squared over R squared exponential of a -2. So there must be 2 there. So the energy lost, first of all, let me take that R out. So there is an R in here, the integral from 0 to infinity of epsilon squared over R squared times the exponential of -2 times T over RC dt, okay? One of the R's cancels this R, and I'm left with an epsilon squared over R epsilon squared over R, the integral from 0 to infinity of an exponential of -2T over RC dt. Again, I have to integrate an exponential. All I have to do is, first of all, multiply by -RC over 2. And then the integral of the exponential is, if you want to do a change variable to u, where u is 2t over rc, and the boundaries of integration should not change, because when t goes to infinity, so is u. When t goes to 0, so is u. So in this case, you can do it by that way, and it's going to amount to the same thing. The only thing is, you're going to pick up an rc over 2 with a negative sign in here if you want to, for the u, and that's going to be the same thing. So what I'm going to do in here is multiply by rc and divide by 2, which is the exponent, times epsilon squared over R, and the integral from 0 to infinity. Now I did it already, so it's going to be the exponential itself of minus 2t over RC evaluated between 0 and infinity. Again, there is a cancellation for the R's. The R and the R cancel, and this exponential at infinity is 0, and at 0 is 1. So again, it's the same thing. Minus C epsilon squared over 2 times 0 minus 1. And this amounts to the expression that as I thought it should be, and it is. So this is how much energy was actually lost in the resistor. So this checks. So we did a full account of the energy. So indeed, 1/2 of it was gone to charging the capacitor, and the other half was wasted in heating the resistor. So that's basically the full story. So this is how much we drained energy, this is how much we stored useful energy, and this is wasted or lost to the environment in the form of heat. Okay, so this is an example of how to, this is actually part of the lecture too. So this is not an example, by the way. This is the charging of a capacitor. We still have another aspect to the problem, and that is discharging the capacitor. Let me give you, I know we still have about 7 minutes, but let me give you a brief look into how this looks like, okay? So this is an animation that I have done with the GeoGebra, okay? Let me pull all the stuff with it. So in this case, I took a resistors of 10 ohms, capacitance of 0.2 farads. And if you do this one, I mean, I didn't talk too much, and we're going to talk about it in the lab, about the time constant. And the time constant is RC itself. It's the product of R times C. So the product of these two should be 2 seconds. In this example, the EMF is 10 volts. And the signal in here for the battery changes. This is actually a square wave, what is it, power source, power generator. So at some points it's 10 volts, and then it drops back to 0 volts. The whole thing takes about 24 seconds, okay? And then it repeats itself, actually. This is not a constant EMF per se. It's constant only during a certain stage and then drops to zero. So during a certain point, you're building up charge in the capacitor, exponentially, of course. And then when you cut off the power, then in this case, it's actually discharging the capacitor. So during this entire stage, it's just charging the capacitor. So if I come to this expression, for example, and play around, for example, with my voltage, where is my voltage? If I come in here to the EMF and make it slightly bigger, so the entire thing will, oops, why is this? So how much EMF I have now? I have 5.6 volts, okay? So now you will see that the EMF has control over this. So depending on that, that's not important as much as, for example, if I make this 20, so the time characteristic now should be 4 seconds instead. So this will extend over which the period is going to happen, as you can clearly see. So I can, oh, I made it 40, not even 4. Sorry. Okay. Oh, was it 40? Yeah, that's fine. Okay. So that's basically how it is. So if I go back into how much it was, and I don't remember how, I think it was 10. Oh man, cannot type these things. So this is how the charging. Now the time characteristic, and we still have about 4 minutes. The time characteristic tells me how much, if I wait 2 seconds, which is tau itself. In this case, why does it drop to 52%? Yeah, it's if I wait long enough, and here the EMF is not. Let me put the EMF back to 10. Okay. It's incorrect. I have to really. The algebra is a little. So this is more. Oh man, I cannot put something in here. Sorry guys, I need to control this. Okay, let's keep it in here. Anyway, 63% when tau is equal to when the time is equal to tau. 98% actually, not 99%, when you are at about 4 tau. Okay, 4 times this number, which is 8 seconds, meaning that the charge will drop after 2 seconds to 37% left. How much charge in it? If you wait 4 times this time characteristic in this example, it's 28 seconds. The reason why I got a different number, because I was using actually wrong math in here. I mean, if you look at it, I was actually multiplying by 10, and that's not correct, okay? That's why if I use a different value other than 10, it's not gonna give me the correct percentage, okay? The mistake is actually in this diagram for different values of this voltage, okay? So I probably should go and correct this one. But the point I'm trying to say in here is always after, if you wait 1 time characteristic, if you wait 1 time characteristic, you're going to have about 63% charged. Or if it was charged, you're going to have only 37% left in the charger, in the capacitor. If you wait 4 times as much, it's going to be 98%. So this tau, which is the product of RC, dictates how long do you have to wait for it to be satisfactorily charged. So it's not really fully charged. It can never be fully charged because t equal to infinity is a huge amount of time. So there is no such a thing. Practically, you would say, okay, how long would I have to wait to actually say I am actually at very, very high percentage of charge? Let's say, for example, anytime it's more than 95%, I'm good. Then in this case, all you need is just 3 times tau. So you have to do for this circuit, which is not a practical circuit. As a matter of fact, practically C is of the order of microfarad, which means that time tau will be of the order of a millisecond. Okay, so if you wait 3 times that much, you're waiting fraction of a second basically, and before you know it, the capacitor is charged. And the energy is almost exactly what we calculated. So that t equal to infinity and the integral is not, in practice, all you have to do is probably wait 1/10 of a second. That's how much it is to do the calculation. And it's going to match with an error, impeccable error. So in other words, the math, the theory, and the practice are 2 different things. When you're doing this thing in the lab, you will see actually charges very quickly if you really are. That's why the lab this afternoon will have the symbols in it in the microfarad, but I actually had to change it to of an order of almost a farad to make this thing looks from our simulation to work at slow motion enough so that we can trap it. Okay. In practice, no, we don't have to do that. We can let the thing come up with the values, and then we can trace them to find them. Anyway, we'll continue this discussion on Wednesday anyway before the discharging of the capacitor. And I guess I will see you in about 20 minutes at 2:30 for the lab. And I will see you guys again, okay? And we'll defer questions later on.